Morning, good afternoon, or good evening, whatever the case may be. In this video, we're going to work on Calculus Section 1-3, evaluating limits analytically. In the last video, we did numerical tables and graphical approaches, but now we'll do a little algebra. Before we get started, let's have a little algebra review here. Here I got a couple things I want to multiply out, 2 minus root x plus 3 and 2 plus root x plus 3. It's a conjugate pair. We got a subtraction and a sum of the same terms. So if we FOIL, the middle terms will cancel. So first times first, 2 times 2 is 4. Again, the outers would be a 2 times the radical. The inners would be a negative 2 times the same radical. They would cancel. Now, here's why I chose this specific example. We've got a negative times a positive, so this is going to be negative. When we multiply radical x plus 3 times itself, we're squaring it, so the radical disappears. But don't forget that radical was a grouping symbol, so the x plus 3 is a group. When we FOIL it out and the radical disappears, it should also be kept as a group. From here, we could distribute the negative and collect like terms. That would just be 1 minus x. So be careful that radical is a grouping symbol, and they should stay grouped all the way through the problem. All right, back to calculus. This is a big section. We got some bullet points here. Evaluate a limit with the properties of limits. Develop and use a strategy to find limits. And then we'll look at some specific techniques, the dividing out technique, the rationalizing technique. And we'll also talk about this thing called the squeeze theorem. Now, the first, I'm going to throw a lot of theorems at you here. I think it's theorems 1 through 6. Are all about direct substitution. Basically, in calc class, when you are told to evaluate a limit or find a limit, the first thing you should always try is direct substitution. Because if you directly substitute in and you do not get divide by 0, you got the answer and it's that easy. The trouble is when we get into dividing by 0, especially 0 divided by 0, we got to try other methods. But again, the first 6 theorems, there's a lot to them, but they always just boil down to always try direct substitution first. So let's see what the book says. In the last section, you will learn that the limit of f of x as x approaches some number c does not depend on the value of the function at that point itself. It may happen, however, that the limit is precisely the exact same value as f of c. In such cases, we can evaluate the limit by direct substitution. That is, the limit as x approaches c of f of x. That little c that comes after the arrow is just going to jump in, and we just get the answer f of c. Such a well-behaved function is called continuous at c. We'll examine this concept more closely in the next section. So again, here are some limits, and these are properties of limits, and these are just saying try direct substitution. Now let me see here. I'm going to start with 2 and we'll circle back to 1. The limit as x approaches c of x. So x is approaching c, so let's just plug that c in the place of x and we get the answer c. What happens if we're plugging in for the base of an exponential? So here we've got the limit as x approaches c of x to the nth power. Well, we're just going to take that c, replace the x with that. That becomes c to the nth power. And then we're done. Now the first one, the limit as, let me rewrite it here, the limit as x approaches c of b is equal to b. Let's think about, I like to tie this one to its graph. If I've got, let's take out that b, get rid of this b, and we'll actually throw a number in there. Like what about the limit as x approaches 2 of 5? If we concentrate on the 5, think about the graph of that. Y equals 5 is just a line horizontal at a height of 5, close enough. And then it says down here we're approaching 2. Well, as we approach 2, if we're here at 1, we're up here at 5. 1.5, we're at 5. 1.9, we're at 5. 1.999, we're up at 5. It doesn't matter where we are along the x-axis, our y value is always 5. So here, that is just going to be our answer. It's like that 5 jumps over, and the limit is equal to 5. And it doesn't matter what number we're approaching down here. This 2 could have been a negative 10 or a 50 or a 5 million. It doesn't matter the approach number. This is going to be our answer because we're just dealing with a horizontal line. Always try direct substitution first. So here, this example one is just tied into those last ones there. The limit of 3 as x approaches 2. Remember, it doesn't matter what the approach number is. That limit is just going to be 3. Here, the limit as x approaches negative 4 of x. Well, if x is approaching negative 4, just plug the negative 4 in. The answer is negative 4. X approaches 2 of x squared. Well, we plug the 2 in there for the base. 2 squared is 4. And there's our answers. Try direct substitution first. Sometimes it works. Now here are some properties of limits. Some of these properties are going to echo throughout the entire course for the whole year. Let's read the setup here to this. B and C are real numbers, and n is a positive integer. So it has to be positive, and it's a whole number integer. F and g are two different functions, and they have different limits. Here, as we approach c of f of x, that limit is the number L. And as we approach the same c value here on g of x, that limit is this other number k. So L and k are just numbers. They're limits. Down here are some of the properties. Number 1, a scalar multiple. So we've got the limit of this number b times f of x. Well, you can sort of mentally drag the b out in front of the limit sign. So we've got the limit of f of x, and we know that limit is equal to that number L. And then we just multiply that number times b, whatever that number is. So we pull out the scalar, we find the limit, and then we multiply the scalar back in. Here we got sum or difference. The limit as x approaches c of f of x plus or minus g of x. Well, it's almost, you could think about it, we distribute that limit notation, and the limit of f of x, that's this number L. The limit of g of x, that's this other number k. So we would add or subtract them, depending on whatever that is, add or subtract. So the limit of the difference is equal to the difference of the limits. Product, if we're multiplying, we have the limit as x approaches c of f of x times g of x. Well, we know that the limit of f of x is this number L. The limit of g of x is this number k. Since we're multiplying them here, we would just multiply those numbers together. It also works for quotients. We're approaching c again, f of x over g of x. Well, the limit of the numerator, f of x, is that number L. The limit of the denominator, g of x, is k. So that's just L divided by k. As long as k is not 0, everything's good. And if it works also for exponential powers. X is approaching c. We have f of x to the nth power. The limit of f of x, remember that's just the number L, and we would raise that number L to whatever the exponent n was. So again, it's a lot of theorems, a lot of f of x's and g of x's, but it's always just saying try direct substitution first. As we'll see here. Now, I think the book kind of wants me to do it one way. Let me see. Yeah, okay. We're going to do this kind of the long way, and then I'll show you the short way also. If we apply the limits very strictly, those properties like they showed us, here we have the limit of a sum. So we can break that into the sum of two limits. We can have the first as the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. For this one, we have that scalar multiple property, so we can bring this 4 out front. So now we have 4 times the limit as x approaches 2 of just x squared plus the limit as x approaches 2 of 3. And now we can do the direct substitution, plug that 2 in for the base x, so that'll be a 2 squared or 4, times the 4 out front becomes a 16. Plus, remember here, if we wanted to plug that 2 in for something, there is no x to plug it in for. So the 2 is irrelevant. Our answer there is just 3. 16 plus 3 is 19. And again, they did that very, rigorously with each step that we saw in those properties. The better way to do it is you just direct sub right from the get-go. We're approaching x is 2. Just plug that 2 in right there. 2 squared is 4. 4 times 4 is 16. Add 3 more, and you get 19. So remember, always try direct substitution first. So this direct substitution property, it's valid for all polynomials and rational functions that have non-zero denominators. Remember, a polynomial is just, like 2x squared plus 3x plus 2. There is no denominator, so a polynomial will never have a chance of division by 0. So the first part of Theorem 1.3 here says if p is a polynomial function, c is a real number, then the limit as we approach c of p of x is always going to be p of c. Direct substitution always works on just a regular old polynomial. Now, if we have a rational function, a polynomial up top, polynomial in the bottom, as long as our denominator is not 0, then direct substitution will always work. We're approaching c of r of x. That's just going to be r of c, and we can rewrite r of c as p of c up top, q of c in the denominator. As long as that denominator is non-zero, direct substitution will not fail. And we'll see it right here. Example 3, find this limit. So we're just going to take that 1 and plug it into the numerator. So our numerator will be a 1 squared plus 1 plus 2. Down in the denominator, we plug that same 1 in right here. So that'll be 1 plus 1. So what do we get? 1 plus 1 plus 2 more is 4. And our denominator 1 plus 1 is 2. And last I checked, 4 divided by 2 is 2. Direct substitution did not fail. What about if there's a radical? Well, direct substitution, again, will not fail. Polynomial functions and rational functions are two of the three basic types of algebraic functions. This next theorem deals with the limit of the third type, the one involving a radical. So here our setup is a little different. N has to be a positive integer. So the index of our radical has to be a positive whole number. The limit below is valid for all c's when n is odd, and is valid for when c is greater than 0 when n is even. Remember, under an even indexed radical, you can only have positive numbers. If you're indexed like a third root or a fifth root, you can do that to negative numbers. So here, I'm just going to rewrite a little bigger. The limit as x approaches c of the nth root of x is just that nth root of c. We would directly sub the c in for the x. Again, this is true for if n is even, c has got to be positive. If n is odd, c can be positive or negative. So direct substitution will work even if you have a radical, as long as you still obey the algebraic rules. What about composite functions like f of g of x? There's been lots of those in math. Does direct substitution still work? Absolutely. The next theorem greatly expands your ability to evaluate limits because it shows how to analyze the limits of a composite function. So we have two distinct functions, f and g. The limit of g is this number L. The limit, let me back this up for a minute. Because it's composite, the output of one is the input of another. So here we're approaching c of g of x. That c goes in, we get g of c. That is equal to this number L. So that's the output that here becomes the input. Now this next function, our limit is not approaching c. Our limit is approaching this number L. And then we'll direct sub that L in for f of x, and we get f of L. So then we could write the limit as x approaches c of f of g of x. Here the functions have been composed. That's the same thing as f of the limit of g of x, which is just L, so that becomes f of L. And if that's a little confusing, I think this example here is a pretty good one from the book. I left a little blank space here because let's write this one as g of x. G of x is the limit as x approaches 0 of x squared plus 4. If we do direct substitution, 0 goes in, 0 squared plus 4 is 4. So this output here becomes the input here. Let's call this function f of x. I'll switch over to blue ink. F of x is the limit as we approach 4 of the root of x. Well, we can direct sub the 4 under the radical. We now know that's legal. And the root of 4 is equal to 2. So because g of x is that limit equal to 4 and f of x is that equal to 2, we can conclude that f of g of x, the composite function. Let me back that up. We should have limit notation. The limit as, let me do this. The limit as x approaches 0, that's the first number we approached, of f of g of x, there's our composite. So f is the outer function. The outer function f was the rooting function. And underneath that, the inner function is g. So that's the x squared plus 4. So here, our original approach number was 0. If we plug that 0 into the composite function, 0 squared plus 4 is 4. And that's under a radical. The square root of that 4 is 2. So here in the first part A, we kind of did that in 2 steps. We did the first limit, got the 4 to come out. That 4 was the input here. We rooted that 4 and got the 2. Now we've composed the functions to begin with, so we just do the substitution once. The 0 went in, the 2 come out. The intermediate step was sort of hidden in the middle. Here's another one really similar to that. Let's call the first function g of x. Oops, there's my pen. G of x, x is approaching 3 of 2x squared minus 10. Well, if we plug the 3 in there, 3 squared is 9. 9 times 2 is 18. 18 minus 10 is 8. And that 8, the output of the g function, becomes the input of the f of x function. So f of x, our limit, x is approaching 8 of the third root of x. So we plug in the 8. The third root of 8 is 2. So now we could conclude that the limit as x approaches 3 of our composite function f of g of x. So our outer function f, that is the third rooting function, the third root of x, but we take out the x and replace that with the other function, 2x squared minus 10. So where we did it before in 2 steps, the 3 went in, the 8 come out, that 8 went in, and the 2 come out. Now we should be able to plug in the 3 and have the 2 come out right away. So the 3 goes in, 18 times, 9 is 3 squared, times 2 is 18, 18 minus 2 is 10, and that's under our third root. Third root of 8, we've already established, is 2. So if you run into a composite function, direct substitution should still be tried first. What about the transcendentals? What about sine, cos, and tan, and natural logs and exponentials? Does direct substitution work on those? Absolutely. You've seen that the limits of many algebraic functions are evaluated by direct substitution. The basic transcendental functions, the trigonometric, exponential, and logarithmic, also possess this desirable quality, as shown in this theorem, presented without proof. So for all of these, x is approaching c, so we just direct sub the c in. Sine of x becomes sine of c. Cos of x becomes cos of c. And that works for all the trig functions. Now here, number 7, we have limit as x is approaching c of a to the x power. So now it's our exponent that is the variable, so that c is just going to be subbed in. So that will be a to the c power for a's that are greater than 0, positive values. It also works with natural logs. X is approaching c of the natural log of x. That just becomes the natural log of c. Always try direct substitution first. Ooh, here we go. Let's see if we remember some of the stuff from our unit circles. So our limit, x is approaching 0 of tan x, so that becomes the tangent of 0. What is the tangent at 0? 0. Remember, for sine squared of x, you could think about that as the sine of x, that quantity squared, move the squared out. So we plug in the 0. That's going to become the sine of 0, quantity squared. Sine of 0 is 0. 0 squared is still equal to 0. Letter C. X times e to the x, we're subbing in -1 for the x's. So here we're going to have -1 times e to the -1. Now remember, negative exponents are bad math manners. Where can we put that? Well, let's move it to the denominator. E to the -1 can drop downstairs to the denominator, where it will become e to the +1. Or we can leave that out as an implied exponent. So -1 over e. Letter D, the e goes in, so we have our direct substitution. Natural log of e cubed. Don't leave it like that because we can evaluate this. A couple ways to do it. One, move this exponent down front as our properties of logs allow us to do. So that will be 3 times the natural log of e. And remember, the natural log of e is equal to 1. Natural logs and exponentials are going to cancel each other out. So that's 3 times 1, or just 3. Okay, always try direct substitution first. Now here we're going to start a strategy to find limits. On those previous slides, we studied several types of functions whose limits can be evaluated by direct substitution. This knowledge, together with this next theorem, can be used to develop a strategy to find limits. So here's a big theorem for today. Theorem 1.7, functions that agree at all but one point. And the theorem says, let c be a real number, and let f of x equal g of x for all x's not equal to c in an open interval containing point c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit of f of x as x approaches c is exactly equal to the limit of g of x as it also approaches c. Is that perfectly clear? Okay, let's move on. Now, what this theorem, it's the big theorem for today. It is very important, and the way I read through it there, it's very confusing. What I like to do is we're going to go through an example. We'll dissect the example at the end. We'll come back to this theorem, and we'll go through it chunk by chunk, and we'll break this down, and you'll see how actually simple it is and how elegant this theorem is. So we will come back if I've melted your brain on that one. I think this might be the same first example from the last section. We might have found this limit on a table. And if I recall correctly, they changed this example in the new textbook. I kept this one from the old textbook. I like the old one better. So here we are, example 6. What do we try first? We have just encountered a limit. We try direct sub. So x is approaching 1. So upstairs in the numerator, we're going to have 1 cubed minus 1. Downstairs in the denominator, 1 minus 1. This is not looking good. We've got 0 divided by 0. Indeterminate form. We're in trouble. We don't have a calculator to make a table. We have no idea what the graph looks like. What the heck are we going to do? Okay. Now, if we think back to pre-calc, we have x cubed minus 1 over x minus 1. Now, our denominator is x minus 1. Can we factor the numerator, a cube minus a cube? Absolutely, we can. Remember when we did this in pre-calc, a cube minus a cube will break down into a binomial times a trinomial. So we bring down the first thing that we're cubing, that's an x. We bring down the same sign minus. We bring down the cube root of 1, which is also 1. So we've got the binomial. Bring over the first term and square it. Switch the sign. Now this changes to a plus. The middle term are these two terms multiplied together. 1 times x is x. The last term is always positive. And the last term is 1, so we square that. This will also be a 1. And I guess I could have my limit notation in there. So we tried it the original form, and we got the dreaded 0 divided by 0. So all we've done is factor it. We've not fundamentally changed the problem. We've violated none of the rules of math. We've just factored the numerator, and look what can happen. We can cancel. So I'm going to copy my limit as x approaches 1, and now my function is just x squared plus x plus 1. All right, so we tried direct sub. It did not work. In this case, we factored and canceled. Let's try direct substitution again. And move this up here. All right, and since this is a polynomial, we had a theorem that guaranteed us this is going to work. So the 1 jumps in, 1 squared, plus another 1, plus the 1 at the end. Well, that's equal to 3. So there's our limit. We did not need to make a table of values and estimate the limit. The graph was not provided. We might have been able to estimate it from the graph, but here we factored and canceled. So now let's go back. Oh, let me do this. I think on the next slide here. Yeah, okay. Got two graphs here. On the left is x cubed minus 1 over x minus 1. When we tried direct substitution on this, we got 0 divided by 0. The graph of this looks like a parabola opening up, but remember the number that gave us trouble, 1. If we go up above 1, there's a hole in the graph at a height of 3. Now we factored and canceled the numerator with that term in the denominator, and we're over here on the graph on the right. X squared plus x plus 1. Compare the graphs. They are exactly identical. The same y-intercept, the same parabolic shape going up. The big difference is occurring here. Here at 1, 3, this graph had a hole in it. Here at this 1, 3, that hole has been plugged up. I'll say, this highway had a pothole in it. The road crew come by and patched the pothole. How did they patch the pothole? They factored and they canceled. The hole that was there is now gone. And I just realized at the bottom here I do have a copy of the theorem. So let's go over this again step by step. And you'll see that this theorem isn't actually all that bad. Let C be a real number, and let f of x and g of x be equal for all x values except possibly at that 1. So look at this. Again, the graphs are identical. F of x's graph and g of x's graph are the same, except for at that 1 point. So if that's true, then the limit as x approaches c exists, and they are the same. Here, when we direct subbed after we factored and canceled, out popped the 3. That 3 is the same as the limit over here. Even though the function isn't defined at this point, the limits are the same between the graphs. So to save us all the trouble of making a table or graphing and comparing the graphs, we can factor and cancel and use this theorem. So the graphs are the same except at that 1 point, the 1 point that was giving us trouble. So we use the factored graph to get the answer, the easy way, for the graph with the hole in it. So here's our strategy, 3 steps. 1, learn to recognize which limits can be evaluated by direct sub. And again, you don't have to memorize them, you just try it first. If it works, good. If not, then we try something else. 2, when the limit of our function as x approaches c cannot be evaluated by direct sub, try to find a function g that agrees with f for all x's other than that 1. Like we just saw, try and factor and cancel. Number 3, you could try to use a graph or table to reinforce your conclusion or check your answer. When applying this strategy for finding a limit, remember that some functions do not have a limit as we approach some numbers. All right, here's another simple one, dividing out technique. They sort of spoil the surprise for us. This technique, because the last example 6 in the new book they changed. So here's the first dividing example. I think this is in our new textbook. They're asking us to find this limit. Of course, we know we're going to try direct substitution first. So the negative 3 goes in. Negative 3 squared is 9, plus another negative 3 and minus a 6. Downstairs, x plus 3 becomes negative 3 plus 3. Bad news, 0 divided by 0. We have indeterminate form, so direct sub did not work. But let's try the factor and cancel technique. And the good thing about this, for it to work, they have to give us a clue. If I look at my denominator, x plus 3 is the factor. So I'm going to assume if I can evaluate this limit, my numerator, when I factor that, let me switch to red ink, one of the factors is hopefully going to be x plus 3. Well, how would I multiply and get x squared? This would have to be a 2. What do I multiply to get the negative 6? That would have to be a minus 2 at the end. Now let's check our middle terms just to make sure. The outers are a minus 2x. The inners are a plus 3x. That does add up to the plus 1x in the middle. So the factorization did work. And I used the denominator as a clue. So direct substitution failed us, but we can cancel. And now we have basically the same limit, but it's with a slightly easier function to work with, x minus 2. So if we sub in the negative 3 minus 2 more is negative 5. And let's see if the graph would back us up on that. If we have a squared divided by a first power, that's going to divide to a first power, so the graph should be a straight line. And there's our straight line. The denominator, that x plus 3, though, does cause a hole in the graph at negative 3 because we can't divide by 0. But when we factored and canceled, we were left with y equals x minus 2. That's also a straight line. It goes through -2. It has a slope of up 1 over 1, up 1 over 1. So this blue line I'm drawing is exactly the same, but it does not have the hole at -3, -5. The original highway had the hole in it because of the denominator. When we factored and canceled, the denominator disappeared, and we paved over that pothole. And then direct substitution gave us the answer we were looking for. Now, in example 7, is that the last one? Yeah, in example 7, that last one, direct sub produced a meaningless fractional form, 0 divided by 0. An expression such as that is called indeterminate form because you cannot, from the form alone, determine the limit. When you try to evaluate a limit and encounter this form, remember you must rewrite the fraction so that the new denominator does not zero out. One way to do this is to divide out common factors. Another way is to rationalize, a rationalizing technique as shown in the next page, on the next slide. First here, a little technology pitfall. Remember, a graphing utility can give a misleading info about the graph of the function. Here's the graph from example 7. There it is on, looks like a TID9 screen. You know it's undefined at -3, but on the low resolution of the calculator, you're not going to see a hole in the graph. There probably won't even be a missing pixel there. On some graphing utilities, the graph may appear to be defined at every real number. However, we know it's not defined at -3. We know the graph should have a hole in it. We can verify this with the trace or the table feature. Again, be careful with those graphing utilities. They're nice, but they're not perfect. Now, another way to find a limit is the rationalizing technique. In pre-calc, we always rationalized denominators. Now we can rationalize either numerator or denominator, whatever needs rationalizing. Recall that rationalizing a numerator means multiplying the numerator and the denominator by the conjugate of the numerator. For instance, to rationalize the numerator of radical x plus 4, you would multiply the both numerator and denominator by the same radical and 4, but with a minus in between them. This is why I use that warm-up, so when we FOIL this stuff out, it'll be a little easier to see. Okay, example 8, we have just found this limit. We're approaching 0. Our numerator is radical x plus 1 quantity minus 1 over x. What do we try first? Direct substitution. So the 0 goes in. We get radical 0 plus 1 minus 1 over direct sub in that x is a 0. So numerator 0, denominator 0. Indeterminate form, we can't get the limit that way. So here we are going to rationalize. And actually, I'm going to drop my limit notation. I'm probably going to need to use the room. So here I'm just going to copy the original problem. Radical x plus 1 minus 1 over x. And we are going to multiply the numerator and the denominator by the same conjugate. Radical x plus 1 plus 1. Radical x plus 1 plus 1. Okay, now in my warm-up, I had the radical second and a minus in there just to give you a warning about those negatives. Here it's not so bad. So we've got radical x plus 1 times radical x plus 1. That is going to equal x plus 1. And then the outers and inners would cancel. The negative 1 times the positive 1 is minus 1. Aha. And then downstairs, my advice, we could distribute the x to the radical. We could distribute the x to the 1. Do not, we rationalized here the numerator. Do not distribute in the other, in the denominator. So I'm going to leave this as x times my conjugate in a set of parentheses. And usually this is a helpful step. You'll see why shortly. So here we're down to this stuff in the black ink all the way to the right. I'm going to get rid of this over here, our work that got us there. And that way I can put back in my limit notation. The limit is x approaches 0. So now we tried direct sub. It didn't work. So we've tried this rationalizing technique. Let's simplify a little. I still want my limit stuff here. X is still approaching 0. In the numerator, this is x plus 1. I put it in parentheses, but I didn't really have to. It's first power, so we can drop them. So this is just x plus 1 minus 1. The plus 1 and minus 1 cancel, so our numerator is just x. Downstairs, we have x times our conjugate. Now it's a good idea we can see why it was a good idea not to distribute that x in the denominator. So we can cancel. We can cancel these out. X divided by x is 1. Now, a common mistake, some people might forget that x was a placeholder. There is still a 1 up here. So this is now 1 over the conjugate. So to recap, we tried direct sub. It did not work. Here we rationalized, and now we simplified. Let's try direct sub again. We can plug the 0 in for this x, so our numerator is just a solid 1. And then we have down here radical 0 plus 1. That's a 1. Plus another 1. So this is 1/2 is our limit. Okay, we did that work. We did some algebra. Maybe we're a little not very confident in our limit being 1/2. We could verify with a table. If we went back to the last section and tried a table on this, we put this function in the y editor of the T99. We go to the table feature, and we start approaching 0. Let's just go real close to 0. Negative 0.001, positive 0.001. Here we're a little above 0.5. Here we're a little bit below 0.5. So right in the middle would be 0.5. or 1/2. Hit the F menu on that T99. You'll go to the graph. Here's what the graph of that is going to look like. Now, your graph would not have an obvious hole right there, but you'll see the graph at 0 is going to cross between 0 and 1, and you could eyeball that and say it's about right in the middle. So we could, verify our algebraic answer by using a graph or a table. All right, up next is the squeeze theorem. This next theorem concerns the limit of a function that is squeezed between two other functions, each which has the same limit at some given x value. So let's see here, the squeeze theorem. If h of x is less than or equal to f of x, which is less than or equal to g of x for all x's in an open interval containing point C, except maybe at point C itself, and also if, let's say h of x, let me do this, here's h of x on the left, that h of x has a limit of L, and way over on the other side, g of x, well, g of x also has a limit of L, then the limit of f of x, the one in the middle, also exists, and it's also equal to L. Okay, graphically, I think, let me even just draw this as we go. So here, h of x is less than or equal to f of x. So we know h of x is always on the bottom. H of x is always underneath f of x and g of x. G of x is always on top. Let me even switch to a different color ink. G of x is on top. And then f of x is always in the middle. And here where these are pinched together, this is our point C. Our x is approaching point C, so g of x and h of x both have the same limit. So if we were to take this over to the y-axis, we would have our limit L. Back to the inequality that set this all up. H of x is less than f of x is less than g of x, so we know f is always in the middle. If I start like here, I know that if I draw g or f of x in blue ink, I have to stay between the red ink and the black ink. So as I'm coming in here, I'm getting pinched. I'm getting squeezed in between because they're pinched here together at point C. When I come out on the other side, I just got to stay in between the red and the black functions. So they call this the squeeze theorem because g of x and h of x squeezed f of x in between them at that same point. So we're assured, again, that the limit does exist. It does exist, and it's also equal to L, just like the other theorems. Now, in this class, we don't do many proofs by, proofs all the way through. I do like this one. It is a slick little proof, and it's geometric based. I really like how this one was put together. So a quick proof of the squeeze theorem. And actually, I'm going to make a quick copy of this slide and move it to the other page because I want to write on some stuff. Paste that in there. Okay. So here, this looks very similar to unit circle. We've got a radius of 1. We've got some stuff on the unit circle. So let's, I had my pen upside down. There we go. So So as we're going around the circle, this point down here, yeah, this is 1 unit. So that would be point 1 comma 0. Remember, if we come up here and we're on the unit circle, remember each point on the unit circle is also an ordered pair. So that point is cosine, ooh, that's an ugly S, cos, comma, sine. So the x-coordinate is the cos, the y-coordinate is the sine. So notice here we go outside the unit circle. Now in our pre-calc class we did not go outside the unit circle, but think about from angle theta's perspective. If we want the y value there, we know the x-coordinate is 1 because we've come out 1 unit and this triangle is going straight up. Think about from angle theta's perspective, we want the opposite side over the adjacent. Opposite over adjacent is tangent. And since our adjacent side is 1, that would be tan over 1 or just tan of x. So there's some stuff that sort of set us up here. We've got, again, our unit circle, and we've gone a little bit outside the unit circle. Let me switch over to here. If we're going to pull 3 shapes out of that, first, the overall big triangle that goes outside the unit circle is here. We're going outside the circle. And next up, if we just take this sector, you know, we've got this sort of triangle coming out, but we keep the curvature on the end of the circle. That's our slice of pizza in the middle. And then if we cut off the curvature on the end of that slice of pizza, you know, we straighten that off and turn that into a triangle. Now, the basis of this proof, and I don't think anybody watching this video is going to argue with me about this point, the area of this big triangle is always going to be greater than or maybe possible equal to the sector area here, and this sector, after we sliced off that edge, will always have more or maybe almost equal to the area of this last triangle. So if we look at the area of each of these geometric shapes, the biggest one is on the left, medium is in the middle, the smallest one on the right. And now let's think about the area formula for a triangle. This area of a triangle is 1/2 base times height. Right? This one isn't too bad. Our base is equal to 1. And the height of that triangle is equal to tangent. Because we found that when we extend beyond there, our y-coordinate there was tan of theta. So what we have is 1/2 times 1 times tan, or let's just write that as tan of theta over 2. Tan theta over 2. That value, you know, we can do this for any value of theta. As we change angle theta, all these area changes, but the basic inequality stays true. This is always greater than or equal to. We have the area of a sector. Think back to pre-calc. We had that slicker, easier formula. As long as theta is in radians, the area of that is 1/2 times theta times the radius. Our radius, conveniently, is 1. So this just becomes half theta, or theta over 2, area of the sector, which is always going to be greater than or equal to here. We're back to a nice triangle. Area equals 1/2 base times height. So that's 1/2. The base here is 1. And the height, remember, this would be our point on the unit circle. That y value is sine theta. Sine theta. 1/2 times 1 times sine theta is sine theta over 2. Sine theta over 2. So again, we established that the area of these shapes will always be true. We've now translated into some geometric formulas, and these will always be true even if we change theta. If theta gets bigger or smaller for all of these shapes, these inequalities will still be true. Where the equal to parts come in, if we squeeze theta down to approaching 0, these would all approach 0 and all become close to being equal. Okay. Now, at some point, our mathematical forefathers got here and decided, okay, what the heck should we do next? And actually, let me shrink this up a little bit. So we can take a fraction, and if we multiply the numerator by something, that's legal as long as we multiply the denominator by the same thing. So at some point, somebody come along and say, I'm going to put all this in a set of brackets, and I'm going to distribute a 2 over the sine of theta. Now, when we distribute, that's going to hit each of these. Now, notice that this 2 in the numerator is going to cancel the 2 in the denominator as all of these distribute. So that's a neat little property that's always going to happen. So here we distribute, the 2's cancel. We're left with tan theta over sine theta, which is always greater than or equal to. Again, here we distribute, the 2's cancel, so we're left with a theta in the numerator and a sine theta downstairs, and that is always greater than or equal to. Here we distribute, so we've got the 2's on the diagonal cancel, the sines on the diagonal cancel. Here we go, so that's a 1. All right, we're getting somewhere. Now, think back to pre-calc. Tan theta over sine theta. We spent a couple sections simplifying trig identities. So sine theta downstairs is going to stay sine theta. But how can you rewrite tangent? What's another alternate way to write tangent? Tangent is sine over cos. So we've got sine over cos all over sine. Remember that sine we can put over 1, bring it up, and flip it. So now we bring it up, we're going to multiply by 1 over sine. Ooh, and look at that. The signs on the diagonal cancel. So what we're left with here is 1 over cos. 1 over cos. So this becomes 1 over cos theta is greater than or equal to theta over sine theta is equal to 1. And I'm going to write it as 1 over 1. Because there's another property here we can always do in math. If we got something like this, that should not be equal to, greater than or equal to. We can, if we flip over one of the fractions here in our ratio, we would flip over all of them. So here 1 over cos now becomes cos over 1, greater than or equal to. We can flip this over. Now it's sine theta over theta, greater than or equal to 1 over 1. We flipped it over. It is still just 1. Okay, last thing here. Let's let our limit approach 0. So I'm going to move this over here, switch to red ink. Let's let the limit as theta approaches 0. So this one here on the left, that's going to become the cos of 0, and the cos of 0 is equal to 1. That's greater than or equal to, let's leave this as sine theta over theta. And at the end, we still have greater than or equal to 1. So if 1 is greater than or equal to sine theta over theta, which is still greater than or equal to 1, we've gotten sandwiched in between. We've got squeezed in between. Since this is 1 equal to this equal to 1, sine of theta over theta also has to equal 1. And let me write this out in all its glory. The limit as theta approaches 0 of sine theta over theta is equal to 1. Or you could write it with x's. The limit as x approaches 0, sine x over x is equal to 1. That should just be memorized. This is one of 3 special limits in Theorem 1.9. This is something, if you're taking the AP test, you should be expected to have memorized. So, I made that a little too big. The limit as we approach 0 of sine x over x is equal to 1. Number 2, as we approach 0, 1 minus cos x over x is equal to 0. And the third one, as we approach 0, 1 plus x quantity to the 1 over x power, that limit approaches or is equal to e. Remember that 2.72, approximately that exponential base. And let me point out here, this does pay dividends in the homework and later in class. The first one here, you can flip upside down. If I make this equal to 1 over 1, I can flip this over. So you could say the limit as x approaches 0 of x over sine x is also equal to 1. You can't do that for number 2, though. Here, if I put this 0 over 1, if I flip this upside down, put the x up top, 1 minus cos downstairs, I would have to flip this over. Now it's 1 divided by 0. So number 2, you cannot flip over. Number 1, it is legal, and it is sometimes very useful that, if you realize that's just upside down, as long as you're approaching 0, the limit is still equal to 1. Example 9. What's going on here? It says find the limit. X is approaching 0, tan x over x. Of course, we should always try direct sub first. So if we plug in 0, you get the tan of 0 over 0. Tangent of 0 is 0. So that is the dreaded indeterminate form, 0 divided by 0. So we got to try another approach. We've got tan x over x all divided by x. Let me just write it here again. Tan of x over x. Let's just start, trying some math that we know. Okay, what's another way to write tangent of x? Well, we've done that before. That is sine x over cos x. Now I'm going to switch over ink so we can see, we've still got this divided by x. I'm going to do divided by x, and I'm going to put it over 1. Because sometimes it's useful, to get everything all on the same line. Since this is a fraction over a fraction, I can bring this up here and flip it. So now I'm just going to rewrite it here. I've got a sine x over a cos x, and then that's times, since I brought it up and flip it, it's now 1 over x. Now, I said this a lot in pre-calc, and I'll say it here in this part in class. We've got some fractions here multiplied together. We can rip this apart and put the pieces back together however we want. Like this first term, we can actually break that into 2. I could write that as a sine x over 1, and then the other one would be a times 1 over cos x. See, I just broke it apart into 2 components, and then I've still got this times 1 over x. So here we've pulled this apart into all its component pieces. Can we reassemble any of these pieces together to get one of these theorems? So if we see it, we can reassemble this piece times this piece. So sine x over 1 times 1 over x, well, that becomes sine x up top, and x downstairs times 1 over cos x. And now I can put I got my room, I can put my limit notation back in there. The limit as x approaches 0. So we've got the limit of these two things multiplied together. So remember we had that in the last video, I think it was. We can look at this now as, or no, it was in this video. We can do the limit of this product is the product of the limits. So I can do this first limit, the limit as x approaches 0 of sine x over x, and multiply that by the limit as x approaches 0 of 1 over cos x. Okay. Now remember when we tried direct sub, we got 0 divided by 0. So now we've done a little algebraic manipulation, and we've seen part of this problem. Now we could use that theorem on. So this piece, as we approach 0 of sine x over x, we have a theorem says that's equal to 1. So now it's 1 times this limit as we approach 0 of 1 over cos x. So let's try direct sub here. This part might have been the part that gave us trouble. We've used the theorem to turn that into a 1. Let's try direct sub here. So now this becomes 1 over the cos of 0. What's the cosine at 0? That's a 1. So this becomes 1 over 1 times 1. That's equal to 1. So we found our limit. Maybe we're skeptical. Maybe we think we made a mistake. We could do, and I wish I saved this from the textbook, we could do a numerical solution, just with a table of values. We could punch this into our TI-89, make sure you're in radian mode. Everything in calculus is always in rads, never degrees in here. And let's just, I'm going to do, I got it written down here. If we go really close to 0, because that was our approach number, x was approaching 0. And let's just do like negative 0.1 and positive 0.1. So if we just do a couple of those values, negative 0.1 gives us an output of 1.0033. Positive 0.1 gives us the same value, 1.0033. Now remember, you think that might be the limit, but remember sines and coses, tans, these are have functions with curvature in them. So what we might have is like here the bottom of a valley, where on either side of 0 we're a little bit above it. So these are both positive, 1.033. Our answer was 1.000. So yeah, if we round each of these down a little bit, maybe we were at the bottom of this valley, we found that limit. And what's next? Example 10, limit involving a trig function. So we're approaching 0, sine of 4x over x. If we tried direct sub like we're supposed to, this will be the sine of 4 times 0, so that'll be the sine of 0 over 0, and the sine of 0 is also 0. So there's that indeterminate form again. Now here, this is a neat example for how you can tweak a problem to get it to fit one of our theorems. So remember, if we have the sine of x over x, or think about it more generically as the sine of something over that same something, if our limit as we approach 0 of that, that's always going to equal 1. So if we look at this problem, we're pretty darn close. This is a sine of 4x over 1x. We want the sine of 4x. If this was a 4x, it would be perfect. So let me do this. We've got our x is approaching 0. I've got the sine of 4x over x. Now, again, this would be real simple if I could just multiply through here by 4 and the problem would be over. But if we multiply the denominator by 4, we've changed the problem, unless we also multiply the numerator by 4. That way we could just cancel them and say that's a 1. So if we do this, 4 in the numerator, 4 in the denominator, we've basically not changed the problem at all. We've changed a little bit how it looks, but the substance is still the same. So we had a property of our limits that says, since we have this constant 4 here times this, we could just sort of pull that out front. So now the 4 is out front, and now we just have the limit as we approach 0 of sine 4x over 4x. Now what I have here in the brackets, let me hit them in red, in these red brackets, we're approaching 0. Sine of something over the same something, that's always going to turn into a 1. So that turns into a 1, and we're multiplying it by this 4 that we took out. 4 times 1 is 4. And here's the graph, what that would look like if you bring it up on the TI-89. Again, make sure you're in rad mode. But we're approaching 0, so that would be the y-axis. And we could either count the tick marks, 1, 2, 3. It looks like we're hitting right about 4. Or you could use the trace feature to better see that value. And that's it. Here, maybe we can probably do some odd problem. Maybe I'll make another video to do some odd problems similar to your evens. But that's ending the video here for 1-3, finding limits analytically.